Over the last few lessons, we have fired a ball vertically upwards in an accelerating elevator. What would happen if we fire it as a projectile with an initial velocity of v0 with respect to the elevator at a launch angle of theta? Let's first find the time it would take to land back on the floor of the elevator. And this is how it would appear. So the full parabolic path will not complete as the elevator accelerates upwards. The ball is fired at an angle of theta at level x, and it lands back on the floor of the elevator at level y. And let's find the time taken to land back on the floor of the elevator. Think about it. We need to consider only the y component of the velocity and the acceleration, as we would know the initial and final y displacements. So we solve independently along the y-axis as we do in projectile motion. The vertical motion of a projectile launched with an initial speed of v0 with respect to the elevator at an angle of theta would resemble that of a ball thrown vertically upwards with a velocity of v0 sine of theta with respect to the elevator. And we take advantage of the fact that the initial and final displacements are zero, since the ball and the floor of the elevator start off together at x, and eventually the ball lands back on the floor of the elevator at y. And we plug this into the second equation of motion, and we obtain the time as 2 times v0 a with respect to e times sine of theta over g plus a, where v0 a with respect to e times sine of theta is the y component of the initial velocity. The difference between a projectile and a ball launched upwards is that for a ball launched upwards, the numerator was 2 times v0 a with respect to e, whereas here v0 a with respect to e is replaced by v0 a with respect to e sine of theta, the vertical component of velocity. Let's find the maximum displacement between the ball and the floor of the elevator. Now we use the concept that in this condition of maximum displacement, the relative velocity between the y component of velocity of the ball and the elevator velocity will be zero, just like we did when a ball was launched vertically. And when we substitute that into the third equation of motion, we obtain the maximum displacement as v0 a with respect to e squared times sine squared theta over 2 times g plus a. The difference between a projectile and a ball launched vertically upwards is that for a ball launched vertically upwards, the numerator was v0 a with respect to e squared, whereas here v0 a with respect to e is replaced by v0 a with respect to e sine of theta, the vertical component of the initial velocity. And remember, this may not be the highest position of the projectile in its flight, but this is the maximum displacement between the ball and the floor of the elevator. And what will be the time taken by the ball to get to this position of maximum height? We use the same concept that is, in the condition for maximum displacement, the relative velocity between the y component of velocity of the ball and the elevator velocity will be 0, just like we did when a ball was launched vertically. And when we substitute that into the first equation of motion, we obtain the time as v0a with respect to e times sine of theta over g plus a. So here again we find that the only change in comparison with a ball thrown vertically in an elevator is the sine theta component of velocity. Everything else remains the same. When a projectile is launched from the floor of an accelerating elevator, the only change we have to make is to replace the vertical relative initial velocity with the y component of the relative initial velocity of the projectile. This change is applicable to the time of flight, the maximum displacement, and the time taken to get to the maximum displacement.